Okay, we've got 1:30, so why don't we get started? Good afternoon, Research Methods. Wow, that's a pretty good response for a Tuesday on week number 7. I hope you're enjoying this great spring day, fall day. I'm thinking a little too optimistically here. Okay, a couple of announcements. First, we had some really great news. Thank you all for your responses yesterday. We spent the first few moments yesterday filling out this consent form that would allow us, if we all agreed, to take advantage of a data set that I think you're going to find really interesting on the so-called NESI, which is the National Survey of Student Engagement. And we have some Denison data that the folks in student development have made available to us. And it turns out that 16 out of 16 of us agreed to play by the rules. Who's heard of the expression before, what happens in Vegas stays in Vegas? Has anybody heard that? Okay, so what happens in research methods stays in research methods. We're going to make that our rule for using the NESI data. But we actually can use the NESI data because everybody's agreed to it. So once we make our way through a couple of these sessions where we're learning generally about stats, we'll use some actual data from actual Denison students. I think you'll find it really, really intriguing. So thanks for your participation in that. All right. Lots to do today. Why don't we do it this way? Why don't we go back to 10.7? That was yesterday's PowerPoint, and we were having a conversation about inferential statistics and frequency distributions, and we made our way all the way up to z-scores. Okay, so we were about half the way through when we ran out of time yesterday. Okay, so I wonder first if somebody could help us out by explaining what is a z-score and also why a z-score might be important. Anybody want to help us out with that? Either of those issues, what it is or why it's important. Okay, we'll go with Brittany first and then Natalie after that. You want to go first? Okay, Natalie, can you help us out?
Z-score is a standard deviation from the mean.
Perfect. Okay, a standard deviation from the mean. All right. Mm-hmm. And we like that in Gaussian distributions because we know that Gaussian distributions have certain mathematical properties. Can somebody help us out why z-scores are important? Do you want to try that one, Brittany, or are you not so sure? So it's okay if you're not entirely clear. We mentioned this the other day. No? Okay, why don't we go with Hannah?
Because they can go across dimensions.
They can go across dimensions, okay? Can you say a little bit more about that? That's actually perfect.
You can measure two different, things that have different units and compare them.
Perfect, okay. Items that have different units, right? They can be compared directly. So I think the example we gave yesterday was height and weight. And if you're a developmental psychologist and you're looking maybe at newborn babies and you're looking at their physical development and how it might relate to their cognitive development or their social development, you might be taking data on height and weight, and you might want to know the relative heights and weights. Of course, you wouldn't be able to compare centimeters to pounds directly, but with a dimensionless unit like the z-score, we can begin to understand where a given child is in either of those distributions, and we can make some pretty direct comparisons. So it allows us to compare apples to oranges, which is really a pretty neat way to go. Okay. All right, let's see if we can move a little bit further into our discussion, and we'll see if we can start to compute the z-scores. There was a formula that we mentioned in the video for today's session, and the formula that you'll use, and this is one that I would like you to memorize. In many cases, you don't have to memorize formulas for this particular course, but here we would like you to memorize the z-score formula. Okay, and we'll just remind you that a z-score is a standard deviation. The other component that we'd like you to remember is the IQ distribution. The IQ distribution has a mean of 100 and a standard deviation of 15 points. So if we're talking about the positive 1 z-score, we're 15 points above that mean. That will put us at 115. If we're talking about being 2 z-scores above the mean, we'd be at 130, and so on down the line. These are some of the examples that we can use to help develop our intuitions about what z-scores are. So here's the actual formula, and some of you might find it easiest just to memorize one of the two, and then some people are really good at algebraically moving these items around. And you're really good at just understanding that by the golden rule of equations, we can do something like multiply both sides of the equation by the standard deviation, and we wind up with this. And then we can add a mean to both sides of the equation, and we wind up with raw score equals mean plus the quantity z times standard deviation. Okay? So let's see if we can do some examples, just to make sure people can work through this. Some folks really like to plug and chug through every component of these formulas. These are algebraically equivalent to others. Others find this just very, very intuitive. They really don't need to go through all those steps. They just can sort of add and subtract in their head, and either of those is fine. So here's an example that we gave in the video. If the mean IQ equals 100, with a standard deviation of 15, and let's say I've got a friend named Larry, and Larry's IQ is 130, what's Larry's IQ and z-scores? So if you can think that through and raise your hand when you think you've got a response. Okay. We're going to express Larry's IQ and z-scores. Okay, so that's what we know about Larry. Larry has an IQ of 130. We want to take that 130 and express it in z-scores. We'll see what we get. Raise your hand when you think you've got a response. A couple of folks are coming. Why don't we go with Maddie? Positive 2. How many people can corroborate that number? Positive 2. Okay. And how many people are not sure where that number came from? Thank you for being honest. Several of us are not so sure. I wonder if I can impose on Maddie. Can you begin to walk us through your logic, Maddie, and let us know how you either thought about this or used the formula?
Yeah, so I use the first formula where you take the raw score minus the mean. So
Okay.
you do Larry's IQ score, which is 130.
Okay.
And subtract the mean, which was 100, and then divide that by the standard deviation.
Perfect, perfect. Okay, so if I can just say that some people in the back of the room can't always hear folks in the front of the room. She decided that we were looking for a z, so she used the top score. And we also had all the information that we needed for the right side of that equation. We had Larry's raw score. That was his IQ. Right? That was 130. We subtracted the mean. And what would the mean be? 100. So 130 minus 100 gives us 30. Okay, and we're going to divide 30 by the standard deviation. What was the standard deviation? Okay, what's 30 divided by 15? Okay, so Larry must be 2 standard deviations above the mean in terms of his IQ. Who's following that logic? Can that work for us? Okay. Okay. So after we do a couple of these, it becomes somewhat intuitive. Usually at this time every semester, a student stops and asks me, can you have fractional or decimal z-scores? And you absolutely can. And the examples that we're developing right now will probably use small number integers, but you can actually have fractional values or decimal values. You can have a third of a standard deviation or 0.28 standard deviations. All of those are possible. Okay? All right, so that was our first example. Okay, let's go to a different friend of mine. If the z-score associated with Craig's IQ is -3, then what's his IQ score? Okay, so Craig has an IQ that this time we're expressing as a z-score. Okay, and it's expressed as a -3 z-score. So what is his IQ? Please don't call it out. We'll let you do a little bit of computation. And then when you think you've got an answer, maybe you can raise your hand. We'll give people a moment to plug and chug through that. And when you come up with an answer, can you please raise your hand? Okay, a few people are coming on board. A few are still plugging. We'll give you a moment to work with this. Okay. A couple of folks have responded, and I think I saw Jenna's hand go first. So Jenna, can you help us out with this? The question again is, if the z-score associated with Craig's IQ is -3, what's his IQ?
I got
55. Did anybody else get that number? 50. That's the number that I got. 55. Okay. Jenna, can you help us out with how you did that, or how you thought about that?
I just used the original equation, so I did -3 equals the quantity x minus 100 divided by 15.
Okay.
Multiplied both sides by 15.
Okay.
Added 100 to solve for x, which is
All right, that's a perfectly reasonable way to go, right? Okay, so we're looking for a raw score here, right? So you actually started with the original equation, is that the one on top? Okay, you could also have used this one, and that's fine too. First, how many people followed that line of reasoning? Anybody not entirely sure? It's okay if you're not sure. We will be using some z-scores, and we'll be using similar kind of rudimentary algebraic expressions here. Our mathematics is not particularly complicated, but we want to make sure you can quantitatively reason. Kip has a question or a comment, or yeah.
When I worked through that, I just kind of did it more simply by like adding up 3 standard deviations and subtracting that from 100.
Okay.
Is that kind of like following?
Yeah, that's exactly the way that goes. And thank you for making that point. What Jenna did was fine. What Kip is suggesting is fine. Lots of different ways to get to that same end. So these are all algebraically equivalent of each other. This sometimes helps students. We all are familiar with different kinds of American coins. We know that pennies are worth 1 cent, nickels are worth 5 cents, quarters are worth 25 cents, right? So if I have 3 quarters, how many pennies do I have? If I have 3 quarters, the equivalent in pennies would be how much? In cents, I should say? 75? Okay, right, so in that particular case, each of these coins is worth 25. In this particular case, a coin, you might think of it as a standard deviation, would be worth 15 IQ points, okay? So now we're 3 coins short of 100 because we know he's got a negative z-score for his IQ, so we can take these 15-cent coins and we multiply those by 3. That gives us a negative 45 because we have negative 3 in our z-score, and we can then combine a mean of 100 with negative 45, and we wind up with a positive 55 as our IQ score. Okay? Who's following that? Okay. Any questions on any of that? No? I think we're doing okay? All right. Now, so far, we've set the stage in a very interesting way. We've talked a little bit about height and weight. We've talked a little bit about IQ. When we got to IQ, we learned that we can express a given value in the IQ distribution at least 2 ways. Right? So far, we've talked about these 2 ways. We can talk about the raw IQ score. We said that Larry had an IQ of 130. We computed Craig's to be 55. We can express those same IQ scores in terms of their z-scores. Okay, so you can have the raw score, you can have the z-score. In the next section, what we're going to learn is there's even a third way that you can express a given score within a Gaussian or bell-shaped distribution. We'll be talking about the percentile ranks. Okay? So this is something that we did in the video, and this is something that we'd like you to really take to heart, and maybe this diagram too is one that you should memorize. Okay? And what I like about this is that there's a relationship here between this Gaussian, and there's a similarity to be found between this and something like a right triangle, for example. Anybody want to help us out how this might be related in some way to a right triangle? This isn't a right triangle. But what do we know about right triangles? What do we know about these? Yeah, thanks.
Right triangles, you have 90-degree angles, and if you cut this in half, reasonably would have 2 90-degree angles.
Oh, okay. Yeah, I guess if we cut this in half, we could say we have a right angle. That's actually a good point. That wasn't what I was looking for, but I kind of set you up to answer in that way. So yes, we could cut it there, and we would have a right angle of sorts. Why don't we go with Rachel? See if there's another connection that we might make. Yeah.
I wasn't 100% sure how it connected, but
Okay. Good. So all right triangles are described by a squared plus b squared equals c squared. What do we call that thing, by the way? The Pythagorean Theorem. Who remembers doing that one in high school? Okay, yeah, all hands are up. We all did that. Anybody want to build on the ideas that Brittany and Rachel have started? Kip, did you want to add something to that?
I was going to say that to find an area of the triangle, we would want to have baseline height.
Okay.
It seems like this would also find the area.
Okay, there's a similarity there. We're going to be finding areas, okay? So that's certainly going to be true. And Mira, did you want to add something?
Well, the way the Pythagorean theorem is always going to find the right triangles, the right Gaussian distribution is always going to be 34 or 14.
Perfect. All right triangles, whether they're small or big, blue or yellow, whatever kind of right triangle we might have, it is always the case, it's a mathematical truth, that we have a squared plus b squared equals c squared. Doesn't matter what the triangle is. Here, it doesn't really matter what the Gaussian distribution is describing. If we have a bell-shaped curve and we have a good Gaussian, then these numbers are always going to be true. This could be height, this could be weight, this could be physical attractiveness, this could be IQ, this could be any variable. If it's bell-shaped, it will always have these proportions between 0 and 1 standard deviation down that way, and 1 standard deviation up this way. We'll have 68% of the population. That's true of all Gaussians, just like the Pythagorean theorem is true of all right triangles. This is true of all Gaussians. So these are really nice properties to have because they give us the opportunity to become all-purpose problem solvers. Right? That's what we're hoping to do with our dentist education, is to become all-purpose problem solvers. And if we can make some measurements and find out that we have Gaussian distributed variables, we can figure out who is where in this distribution. And we can describe that by a raw score. We can describe that by a z-score. We can also describe that by a percentile rank. First, by a show of hands, who remembers seeing percentile rank earlier? Okay? All right, so we can think about the percentile rank that we have at any given point here. Okay? Let's see if we can do a couple of questions. What percent of the population falls between z-scores of 0 and negative infinity? We'll let you think about that for a moment and raise your hand when you think you've got an answer. A z-score of 0. Okay? And then here's the negative side, and we'll go all the way out. We'll pretend that goes out infinitely. So what percent of the population falls between those two extremes? Why don't we go with Natalie this time? 50%? Is that what you were going to say, Jenna? Okay, 50%. So we've just cut the distribution in half. Who's okay with that? Okay, so this is, at the 0 z-score, we have the mode and the median and the mean, and we can say that 50% is to the left, 50% is to the right. Okay, so we know that about any Gaussian, whether it's describing height or weight or whatever the case might be. Okay, all right, let's see if we can now give you a couple of variations on this. So if your z-score is 0, what's your percentile rank? Thanks, Mira. 50%, okay? We're at the 50th percentile if your z-score is 0, okay? All right, so that's interesting. Now, we've talked a little bit earlier about IQ scores. We converted them to z-scores, and now we can add on yet another descriptor, and that is the percentile rank. And we can do that because all Gaussians follow this formula, or this proportion, just like the Pythagorean theorem is true for all right triangles, okay? If your z-score equals +1, what's your percentile rank? Can we all yell it out? 84, okay, all right, so this was the first 50, and then we're going to go to +1. We're going to add to that first 50 an additional 34% of the population. 50 plus 34 brings us to the 84th percentile. Who's seeing where that number came from? Okay, so we're getting there, all right? We're starting to see that we can pull out percentile ranks from these Gaussians no matter what they're measuring. If your z-score equals +2, what's your percentile rank? Can we all yell it out? 98, okay, so we're now in the 98th percentile. Remember that this idea of percentile is we're describing the percentage of scores at or below a particular score. If our particular score is z-score +2, 98% would be at that score or lower, and only a remaining 2% would be greater than that, to the right of that on this distribution, okay? Okay, let's see if we can do this. We'll give you a moment and then raise your hand when you can answer this one. A little bit of mental gymnastics here. If your IQ is 85, what's your percentile rank? If your IQ is 85, what's your percentile rank? So now we have to mix and match a little bit and go in and out of, if you will, a few different currencies. The currency of raw IQ scores, the currency of z-scores, the currency of percentile ranks. But there are equivalents across all of these in all sciences, not just the science of psychology. Okay? If your IQ is 85, what's your percentile rank? A couple of hands have gone up, and I think I haven't called yet on Marin. So why don't we go with Marin? The 34%, okay. Actually, I came up with a different number, but we'll see if anybody else came up with a different number. We'll see how you reason about that. I think I see where you may have come from. Who else has a guess about this one? Anybody? Why don't we go with Mira again? 16%, and then let's check in with Kip and with Jenna. That's 16%. Okay, Mira, can you tell us how you came to 16%? And I think Marin's probably going to agree. I think you probably used a similar line of reasoning. Can you help us out with that?
Well,
Yeah. Mm-hmm.
IQ score is 100.
Okay, so right here we would be at the 50th percentile. Would be at z-score equals 0, and be at IQ equals 100. Okay.
So then I took the standard deviation, so 100 minus 15.
Okay, so one standard deviation away would bring us down by 15, and that would put us at an IQ of 85, which is to say a z-score of -1. And can you finish that off for us, Mira?
So then 14% plus 2.
Okay, 14 plus 2. So the percentage of scores at or below a particular score would be these 14 plus those guys. It might have been the case that that Marin was looking right over here. She saw the 34. So I think, is that where that was coming from?
I got -1, so I was looking at it.
Okay, all right. But you were good to get as far as -1, so you got most of the way there. So if your IQ is 85, and by the way, this would be true for the entire American population. If you happen to run into a person or learn about a child who has an IQ of 85, we would know that that child is in the 16th percentile. So that child has an IQ that is as high or higher than 16% of the population, but actually lower than 84% of the population. Okay? All right, who's following that? Okay, so it's really cool that we can mix and match this way. Questions? Okay, all right, so we're going to now begin to use some of that information to help us understand a little bit about hypothesis testing. Okay, and we're going to learn that we can typically think about statistically significantly different scores, something that's significantly different from something else, by taking advantage of these Gaussian properties, right? And we're going to be thinking about this 0.05 that we remember maybe from Intro to Psych. Who remembers doing that in Intro to Psych? And 0.05 was a cutoff value for statistical significance. Okay? So in this Gaussian distribution that we have, we can take the most extreme 5%. and we can divide that 5%, 2.5 down here, and 2.5 up here. So the 2.5 and the 2.5 are going to combine to 5. In the middle, this pink area that we have in this particular slide would be the more typically occurring scores, right? Okay, and then only these most extreme scores over here are going to be in the so-called critical region that we'll see in just a moment. And if we get scores out on that side, we would say they're significantly different from the mean. Okay? Who's following that? Okay, and that's working for us. All right, why don't we see if we can go into Excel, and we'll see if we can come up with a couple of new kinds of functions. One will be called norms_inv, and one will be called norms_dist. And just to say a little bit about that, I have all of this up here, and this is from the video also. We're going to be dealing with the normal distribution. We're going to be dealing with a particular type of normal distribution called the standard normal distribution. And statisticians like this one. This normal standard distribution has a mean of 0 and a standard deviation plus or minus 1. And a lot of statisticians use that. That's the standard normal distribution. And we'll do a couple of commands inside of Excel. So I'll break out of this. I'll ask you to join me in going to any blank Excel spreadsheet. And what we're going to be doing is making some translations between these different currencies that we have. We have the currencies of percentile ranks that we can convert into z-scores, and then we could go from z-scores to standard to raw scores if we needed to. Okay? All right, so let's do it this way. Let's remind ourselves that what we can have inside of Excel would be these different probabilities that we might be interested in, maybe a probability of 0.05 for statistical significance or some other kind of probability. So in cell A1, why don't we put something like probability? And spelling doesn't count. And I'm going to make this a little bit bigger so the people in the back can see a little bit more comfortably. Does that help? Yeah, okay. Natalie gives me a thumbs up on that one. There's the probability. Okay. All right. And then what we're going to get out of here is going to be a z-score. We're hoping that we can go back and forth between the two. I'm going to copy this over to here and say z-score. Okay. And I'll center those. You don't have to center them. You don't have to make them red. Okay. Okay. So we can think of probability as being the same thing as percentile rank in our distribution. We can use those all interchangeably. Okay. And we might be interested, for example, in a probability of, say, 0.5, right, which would be something like the percentile rank that is the 50th percentile rank. So I'll make that nice and big also. I'll turn that green, and I'll make that 28 or so. Copy that over here just for a moment. Okay. And so if I had a probability, which is to say a percentile rank at 0.5, what should my z-score be if I'm at the 50th percentile? Go ahead. 0. Okay, that's going to put me right in the center. Who's with us on that? Is that working? Is that working for us? Yeah. Okay. All right. So let's see now if we can get the syntax associated for obtaining these z-scores. We're going to take advantage of some of Excel's functions. And a function is a rule for turning one number into another number. And this particular function is shown here. It's the normal standard inverse function. Okay, we call that norms_inv. So as always, I'll do it this way. I'll put in equals. Okay. You don't have to put that apostrophe in there, but I put that in there so that it stays as a string variable. We'll put in equals norms_inv. Okay. We'll open a left paren, and I'll let you tell me what Excel is telling you. So equals norms_inv. Okay. You're getting, how many people are getting prompted for a probability? Okay. All right, that's what should be happening. It's prompting you for probability. And so you can do a couple of things. You can either literally put in the number 0.5 there if you like, or if you want to be really bold about it, you can click on A2 and you would pick up the value in A2, which is a 0.5 at the moment. Okay, so you could put that in. I'll do that also. Equals norm_inv. I'll come over to here and I stick in my probability. I'll close that off. And I wind up with a z-score equaling 0. Can I get an amen on that? How many people got that? All right? All right? All right. So yeah, pretty cool that this works that way. So if we're at the 50th percentile, or our probability is 0.5, then our z-score would be 1. Okay? Suppose I wanted to figure out if I could get something close to a positive 1 z-score. Does anybody have an idea of what probability I should stick in to come out with a z-score of about positive 1? Tip's got something? 0.84. Let's give that a whirl. 0.84. Okay, and that just about does it within rounding. Okay, somebody called it the 84th percentile just a moment ago. We said that corresponded to a z-score of positive 1. I'll see if I can call that up for us. Back over here. Back this way. Okay. So a z-score of positive 1 equaled the 84th percentile. Who's okay with that? That work for us? Okay. Let's see if we can do a couple others of these. Okay. Play around with that a little bit further. Let's put in a, how about something like this? How about 0.16? Okay. How many people get this number? Essentially minus 1. Okay, so we just went to the other extreme. Okay, does that work for us? Is that a question or just a comment? Please.
Why isn't it just a solid 1?
Why isn't it a solid 1? Yeah, we had to cheat a little bit there. Actually, the way it works out is that it's really not exactly the case that a positive z-score of 1 is the 84th percentile. It's within 1/1000th of that, but it's not exactly that. It's just a lot easier to memorize when you go up or down by 1. You're at the 84th percentile, the 16th percentile, but you're really not at the 84th. You're at like the 83rd.99. Okay, so it's an adjustment. It's a little rounding simplification. Thank you for pointing that out. Okay? All right, let's see if we can do the other way around. Here we've been sticking in a probability and getting out a z-score. Okay? We can also do the complementary function or the inverse function. We can sometimes put in a z-score and get out a probability. So I'm going to go over to a different sheet and copy this information. If you'll join me now by going over to sheet 2, and we'll just paste that stuff in again. And I'm going to size these out a little bit, and we'll change things around just a tad. What we'll do is, specifically is we'll now put in the z-score. That'll become our input. We'll get rid of that, and then over here what we'll do is we'll get out some kind of a probability. Okay? And to do this, we're going to get a slightly different kind of syntax, but we're still using the normal standard. Okay? And just to make sure you're all on board with this, in the standard normal curve, what was the mean? Can we yell it out? What was the mean of the standard normal curve? I mentioned it once in the video, and I mentioned it once today, but we've been talking about a lot of ideas. The standard Gaussian is centered where on our negative to positive scale? 0. Okay, and what's the standard deviation? It turns out to be 1. Okay, all right, that's some property that we have of the standard normal. It's centered at 0. It has a standard deviation of 1. Okay, we're going to do equals over here, equals norms. So that's the standard normal, and we'll do the distribution function. Okay, and now in this case, it's prompting us for a z, but I'll pause there to make sure people got that. How many people are being prompted for a z? Okay, all right, so if we stick in a 0 z-score here, we'll literally put in 0. Okay, and then we'll close that off with a right parenthesis. Okay, we should be at a probability of 0.5. Does that make sense to people? We're at the 50th percentile, and I'll put in a 0 over here, and I can now change this to not literally pick up 0, but pick up whatever value is in my neighboring cell, and I can now change this to a z-score of 1, and I wind up at approximately the 84th percentile. Kip correctly pointed out that it's not exactly 84th percentile. I can put in a z-score of minus 1, and that brings me down to, if you will, the 16th percentile, given some rounding and so forth. Okay, so we can use these two functions to find some cutoff points and some z-scores for probabilities, probabilities for z-scores, and so forth. Okay? So we're using the normal standard curve in both cases. The inverse and the dist functions basically undo each other. Just like multiplication and division undo each other, addition and subtraction undo each other, squaring and square rooting undo each other, we have the inv and the dist. Here's the distribution function, here's its inverse. Okay? Who's following that? Questions or comments on any of that? Okay. All right, why don't we go back over here? Hopefully people still have this one. Do you still have this one going, the probability and the z-score? Okay. Okay, now you stay there. What I'm going to do is pop this open just for a second. We'll go back to here. All right? And we're actually interested not just in the upper 2% that we might see here, but we really want to know the upper 2.5%. Let me see if I can figure that out by going along here somewhere. Oh, okay, let's say that we want the upper 2.5%. Okay, or the lower 2.5%. Can we use norms inv and norms dist to help us find that? Okay, so let's see, what z-score would be associated with the upper 2.5% or the lower 2.5%? Okay, so what z-score? So remember that if we wanted the upper 50%, right, our probability of interest would be 0.5. We wanted the upper 50%. Okay, so we'd be at the 0 z-score. The z-score that's associated with 0.84 is about 1. Okay? What we want to know is this most extreme 5%. We keep talking about this 5% alpha rule that we've got in science, the 0.05, that's statistically significant. Okay? So the question then becomes, what is the z-score associated with that cutoff value? Let you think about that. See if you can play around with this. We're trying to find the boundary for the upper 2.5%. What separates the upper 2.5% from the lower rest of the curve? Okay, Kip's got an idea. We'll see if anybody else has. Mira has an idea. See if anybody else has one. Mira, what do you have? You have a -2? Okay, that's going to work. That's going to be pretty close anyway. Can you tell us how you thought about that?
I just put in 0.02.
You point at 0.02? Okay, you put it in 0.02, all right, and you came up with something like this. Okay. Now, this would be, that probability of 0.02 would put us at the second percentile. Okay, and that's pretty good. If we take the number 5, we're dealing with a 5% alpha level, 0.05 is our cutoff. What's half of 5? Can we all yell it out? Half of 5 is 2.5, okay? So Mira was almost there, right? She put in 0.02. Suppose she put in 0.025, okay? So that's the lowest 2.5 percentile. We see where that number came from, 0.025, okay? And we get that number. Kip, is that what, did you have something like that, or did you try something else?
I did 975.
Good, okay, that's the same thing. Let's go, we'll come back to this one. So Kip and Mira actually have very similar kinds of logic, 0.975, okay? All right, and Kip, how did you get that?
Because I referred to the PowerPoint Gaussian curve.
Okay.
So at the 2 standard deviation, or the z-score of 2
Uh-huh.
would give you the 98%.
Okay.
And we were looking for to get like the 2.5%.
2.5. So we're not really at the 98th. We're at 97.5. First, how many people understand where the 97.5 came from? Okay. So we're not at the 100th percentile. We're not at the 99th. We're not at the 98th. We're actually not at the 97th, but we're halfway between those two. Right? We're at the 97.5 because we took 5, we divided it by 2. We want the upper 2.5%. We want the lower 2.5%. So Mira was going to put in something near 2%. You can put in 0.025 for the lower end, 0.975 for the upper end. First, how many people are seeing where those numbers are coming from? Is that confusing anybody? That's confusing you? Okay, all right. Can somebody help us to understand that? So we've got the 5%. All right, somebody want to explain how we got to 97.5 and 2.5? Yeah, go ahead, Kip. All right.
I'm not quite sure how to explain this, but we're
So we're just trying to get, so most of us in the room understand where 97.5 is coming from and where 2.5 is coming from. But some of us are a little shaky on that, okay? So any idea, you got to the correct intuition. Trying to now articulate that intuition is a challenge. You want to give it a shot?
Sure. Well, so the z-scores are divided on the Gaussian curve pretty evenly.
Uh-huh.
Except we're looking for a figure that's not so even, which is like not that 2% on the upper end, but it's 2.5.
Uh-huh.
So instead of being like 98% of the data, at 98% of we get 97.5.
Yeah, that's exactly right. No, that's really good. And I'll draw a picture to help embrace what I think is Kip's intuition and also Mira's intuition. So we're looking at this Gaussian curve. And the entire area under that curve is 100%. Okay? The entire area under that curve is 100%. We're interested in what we might call typical scores from the mean. And we might be interested, for example, in the centermost 95%. And we're also interested in exceptional scores, the most extreme 5%. Because we're interested in the most extreme 5%, we can cut that in half because we want to take 2.5% down this way, 2.5% over this way. 5 over 2 gives us 2.5. Okay? So we want to know about this lower 2.5, this upper 2.5. But remember that this upper 2.5 is already not at the 50th percentile, not at the 84th percentile. It's cumulative. It's everything except for this last 2.5%. So 100 minus 2.5 gives us 97.5. Does that work for us? Okay. Yep. Simple addition and subtraction. Now, we didn't have to have a 5% range that we might be interested in. We might have other numbers that we're interested in, but usually we're interested in 0.05 as a standard significance level. Okay? All right. Questions or comments on any of that? Good. Okay, good quantitative reasoning. All right, why don't we do it this way? Why don't we begin to transition into today's PowerPoint? But before we do that, we'll get it set for something that we haven't quite done yet. We'll do a pop quiz as one question. We've done that before, but we'll also give you the opportunity to answer two questions. One is a pop quiz question, and one is a purely extra credit question. Okay, so we're going to give you the chance to get two of these. So if you please put everything away, except for one piece of paper that has your Slater box number on it, we'll give you a pop quiz question right out of our sequence for today, and we'll also give you a chance to answer an extra credit question. The way the pop quizzes work, as always, these are always worth 10 points. You can get between 0 and 10 of those points. And the way the extra credit will work is it'll be 10 points for nothing if you get it correctly, or maybe you'll get a portion of that correctly. So you could have the opportunity today, if you get both of these right, to earn 20 out of 10 points. Okay? All right? So you can increase your numerator in both cases, but the denominator stays at 10. Okay? Okay, so everything away, except for that one piece of paper. And we'll have your Slater box number up top. Okay, and we'll go with this pop quiz question. This is taken right out of the PowerPoint. So here's the pop quiz question. Identify the three factors that determine the power of a statistical test. And we don't need sentences here, just boom, boom, boom. Okay, just spell those, spelling won't count, just spell those out, those three. And then the extra credit question, describe modus tollens using P's and Q's. If you want to punt on that one, no harm, right? Because you can only earn points on that or not earn points. You don't lose points. Okay? So those are the two questions. Okay? No sentences here. You can just describe modus tollens using P's and Q's. You don't even need to have a sentence there. And then identify the three factors that determine the power of a statistical test. When you're done, you can put those three bullet items and the extra credit, if you got down here, face down. Yep, shall I take a moment? You can bring those back. Hopefully this is a quick one for you to do. Hopefully it'll be a quick one for me to grade. We'll get these back to your Slater box maybe even tonight. Most folks have turned their item in. Wait just a moment here. You can put that face down if you like. So if you got both of those, you're golden. You've made 20 out of 10. If you got just one of them, then on some level you earned 50% of the responses, but you still got 100% of the points. We'll put those down here. All right, I think we've got everybody's response. Anybody still not turned in? Ah, thank you, Mike. All right, we got them all? All right, really good. Okay, so let's begin to transition into today's PowerPoint and see what people have to say about this. So now we're up to the 10.8 PowerPoint, where we're doing hypothesis testing. And we've set the stage very nicely by understanding the underlying Gaussian distributions and so forth. Okay? And here's our research cycle that we keep coming back to, where there's something in the real world that we want to pull out. Let's all yell it out. How do we abstract to get the research representation? We need to do two things. What are the two things we need to get the research representation during abstraction? Go ahead, Jenna. And sampling, right? Okay, then we have methodologies. Let's remind ourselves of the three different methodologies that we have. Yell out any of them if you can. Experiments. Actually, sampling is how we get from there to there. Right? Surveys, okay, that's an S, right? And observation, okay? And then we'll be evaluating these hypotheses based on what we know relative to z-scores and percentiles and the frequency distributions that we were dealing with today and yesterday. Today we were dealing with some Gaussian distributions, and we used the normal standard curve. The other day we were looking at some skew distributions. We talked about positive skews, negative skews. We looked at an example of Michael Jordan and how he throws his salary skew off for his particular cohort. Okay, all right. I wonder if we can have somebody tell us a little bit about null and alternative hypotheses. Can anybody help us out with what they might know about null hypotheses and alternative hypotheses? And some of the terminology that we had for today. Okay, we'll go with Jenna. Thank you, Jenna.
Null hypothesis is that there is no relationship between variables.
Okay.
And you always want to start with the null hypothesis.
Okay.
And then the variable is the idea, as you put it, fail to reject the null hypothesis.
Okay, right. No, okay, that gets us most of the way there. So we do have this null hypothesis where there's no relationship between the variables, right? I mean, that's
Variable one is that there is a
yes, and then hypothesis one, the alternative hypothesis would be the case that there is some kind of relationship there. Now, this could be a correlational study, and we say that there's no association between the two variables. That would be a null hypothesis. It could be an experiment where we're looking at whether, for example, Prozac is going to be affecting depression ratings or not. Okay, and we might say, is the independent variable driving the dependent variable? The null hypothesis says no. There's a null effect. And can we yell out, if you can find it in there somewhere, can we all yell out, what's the symbol for the null hypothesis? HO. All right, there it is, HO. And the symbol for the alternative hypothesis is H1. We sometimes call that the research hypothesis. Okay, so those are the two different kinds of hypotheses. And we never actually directly evaluate the alternative hypothesis. We typically evaluate the null hypothesis. Natalie has a comment.
So is the alternative hypothesis finding that there's a relationship between the variables and just not what you predicted it to be?
Nope, we don't even go that far, but we take that first, that was a good start, right? So, and we'll see some examples of null and alternative hypotheses in just a moment. And so the null hypothesis is that there's no relationship between the two. The alternative hypothesis is that there is a relationship. It's that simple. Okay? And we don't actually go and evaluate that for some reasons that might be become evident later on in this session when we're talking especially about modus tollens. Okay? All right, so let's go a little further and see what other kinds of ideas we can get here. So we have our null hypothesis, and we have our alternative hypothesis shown in this one. I'll make this nice and big. Okay? All right, and Jenna got us started on a real good introduction to this. The null hypothesis is shown as HO. There's no relationship between the two. How might we express the null hypothesis mathematically? We know that there's no relationship. How do we typically express the null hypothesis mathematically? Any idea about that? We can do it in symbols. Okay. Here's a little clue up here. Okay. We've got the mu. What does mu typically tell us? The mean, and the mean of what specifically? The mean of a population, right? So we talk about these population parameters. We describe the population by using mu, and what was the other one that we sometimes use? Mu and sigma, right? Okay, so some folks recall that, mu and sigma. These are the Greek alphabet letters that we use to describe the mean and the standard deviation of the population, okay? And then if we had a sample, we might be using the x bar or the lowercase m or the lowercase s to give us the mean and standard deviation of the sample, okay? So one of the ways of talking about HO in just simple mathematics, it might be something like this. We might say HO. HO. We'll put a colon there. And we always start out with this important prepositional phrase. We can say that in the population, all mu's, and I'll make a mu like this, that's a mu, are equal. Okay? That would be one of the ways of describing this mathematically, this null hypothesis. So we'll take a particular case. We'll be looking at the case of depression. And we can measure depression using the Beck depression inventory. This is the example that we give in the video. And maybe the population mean for a hospital filled with depressed patients has a Beck depression inventory score of 26. Okay? And then we try to administer some kind of psychological treatment. That might be a behavioral therapy treatment. It might be a cognitive therapy treatment. It might be a pharmacological agent. And the example that we give in the video, does anybody recall what example we give in the video? What pharmacological agent we use? Prozac. And who remembers what class of pharmacological agent that Prozac is? Particular kind of, yeah, thanks. SSRI, a selective serotonin reuptake inhibitor. Okay, so we could have a behavioral intervention, we could have a medical intervention in the way of Prozac and so forth. And if the null hypothesis is true, that there's no effect between Prozac and our level of depression, then if we start out with a mean of 26 and we administer the treatment of Prozac and Prozac does nothing, what will our mean be after the fact? Still 26. All the mu's will be equal. Pre-test, it's 26. Post-test, it's 26, or nearly so, right? Or nearly so. And we can even draw a little diagram about this. Okay. Here's another Gaussian distribution. We could say that we can have a 26 over here. Here's a low end. Here's a high end. These might be depression scores. I'll put this as BDI for Beck depression inventory. Okay. On the other hand, if it does turn out that the SSRI, the selective serotonin reuptake inhibitor, is working well and really does tend to bring our depression levels down so that we wind up with maybe an extreme score down here. If that score is observed, we would say, you know what, that's probably significantly different from the mean. We can reject the null hypothesis that all mu's are equal. The mean for this particular group would be different significantly from this, and we would say that this is now rejected, and we might then accept H1, I'll put H1 up here, in the population. Not all mu's are equal. And what's interesting about that is we didn't make a directional prediction. All H1 is saying for the moment is that if we do administer Prozac, we're going to wind up maybe in the extremes. We didn't say it would be the low extreme. We didn't say it would be the high extreme. It'd be a shame if we wound up all the way up here. That would imply that there really was an effect of Prozac, but it made things worse. Right? We had higher depression scores after taking this than we did before we had taken it. But all H1 is saying in its present form is that there's no effect, and that's expressed mathematically as not all mu's are equal. At least one of the means will be different from the other. We're really only dealing with two means here, the pre-test condition and the post-test condition. Who's okay with that? Who's following all of that? Okay. All right, so that's a really good introduction to the null hypothesis. And of course, one thing we want to emphasize is this prepositional phrase, in the population. Anybody want to remind us why we use that phrase, in the population? For inferential statistics, why is it the case that our hypotheses for inferential statistics starts out this way? In the population? Thanks, Mira. Yes, right. We might only be able to use a sample in the real world. But that's the practical thing that we can. But we really would like to know about the population of maybe all depressed people. Okay? So we're trying to draw an inference about the overall population based on a sample. Okay? And the overall population is defined as every member of a group of interest. And that might be, in this particular case, something like everybody who's clinically depressed. Okay? Well, we can't really investigate everybody, but we can take a sample, and if our sample is representative, because we know about probability sampling, okay, and we administer our treatment, then we might be able to draw an inference about the population from the sample. Okay? All right, we're at 2:20. Why don't we draw the line there? We'll come back tomorrow, and we'll finish off our 10.8 PowerPoint, and we also have one for tomorrow, 10.9, that I think you'll find very interesting. We'll be introducing the chi-square statistic. So please look through the handout that you have for today, and keep an eye out in your Slater box for the pop quiz. Okay, have a great day. See you tomorrow. Bye-bye. Okay, bye-bye. Have a great day. Enjoy this fall day. Okay, bye-bye.